When most people first encounter the word parsec, their reaction is usually some mix of confusion and mild annoyance. It sounds technical, it sounds unnecessary, and it sounds like one of those scientific terms invented purely to make things harder than they need to be. After all, we already have miles, kilometers, and light years. Why would anyone need yet another unit for distance, especially one that seems to make no intuitive sense? That reaction is completely reasonable. The problem is not that the parsec is strange. The problem is that the universe is strange, and our everyday ways of thinking about distance simply do not survive once we leave Earth behind. On Earth, distance is easy. You can walk it, drive it, or fly it. Even when distances become large, across oceans or continents, they still exist on a scale that the human brain evolved to understand. We have landmarks. We have maps. We have reference points. If someone tells you a city is 500 miles away, you may not feel that distance emotionally, but you understand what it means. Space does not offer that courtesy. In space, distance becomes deceptive almost immediately. The night sky looks flat. Stars appear painted on a dome, all seemingly the same distance away. Some are bright, some are faint, but brightness turns out to be one of the most misleading clues imaginable. A bright star might be relatively close, or it might be incredibly far away but intrinsically powerful. A dim star could be distant, or it could be nearby and weak. This confusion haunted astronomy for centuries. For most of human history, no one knew how far away the stars actually were. Philosophers debated whether stars were tiny lights just beyond the planets, or suns scattered through an enormous void. There was no experimental way to tell, and that is the core problem that leads directly to the parsec. Hi there, and welcome to Sleepy Space Traveler. I'm really glad you're here, and I hope this moment can become a pause in your day. This channel was created as a quiet space for anyone who enjoys falling asleep to calm storytelling, peaceful narration, and soft explorations of science, the universe, and the mysteries around us. If this kind of content helps you relax, unwind, or fall asleep a little easier, I would really appreciate it if you could like this video and subscribe to the channel to help more people discover this space, and help us continue creating these nightly journeys. Please let me know in the comments where you're watching from, and what time it is for you right now. Thank you for being here. Now, let's begin. Astronomy is the only science where you cannot touch your subject, collect samples directly, or move closer for a better look. Everything we know about the universe beyond Earth comes from light. Photons that travel vast distances before reaching our instruments. Those photons carry information about color, motion, composition, and temperature. But distance is not written on them. Imagine trying to judge how far away a campfire is at night. A large fire far away can look exactly like a small fire nearby. Without additional information, your brain has no reliable way to decide. That is the situation astronomers faced with the stars. Early astronomers tried every trick they could think of. They assumed stars were similar objects and compared brightness. They tried measuring apparent sizes. They even attempted philosophical arguments about harmony and order. None of it worked. Distance remained the missing ingredient, and without distance, astronomy cannot progress beyond description. You cannot calculate the true size of a star. You cannot know how much energy it produces. You cannot map the structure of the galaxy. You cannot tell whether the universe is static or expanding. Distance is the skeleton key of cosmology. At first, astronomers hoped that Earth itself could provide a measuring stick. After all, Earth moves around the Sun. That motion should cause nearby stars to shift slightly against the background of more distant ones, an effect known as parallax. The idea was simple. The execution was brutal. The shift is tiny. For even the nearest stars, the angle is smaller than what the human eye can detect without instruments. For centuries, telescopes were not precise enough to measure it. The absence of detected parallax was even used as an argument against Earth's motion. Eventually, technology caught up with theory. In the 19th century, astronomers finally measured stellar parallax. And when they did, the result was shocking. The stars were not just far away, they were staggeringly far away. This discovery did not just add a new number to astronomy, it forced a complete rethinking of humanity's place in the universe. The stars were suns. The void between them was enormous. The Milky Way was vast beyond imagination. And it became immediately clear that ordinary units of distance were useless. Kilometers collapsed into meaninglessness. Astronomical units, the distance from Earth to the Sun, worked inside the solar system, but failed beyond it. Light years helped convey scale to the public, but they were awkward for calculation. Astronomers needed a unit that emerged naturally from how distance was actually measured. That unit was the parsec. The parsec was not invented for convenience. It was discovered, in a sense, as a byproduct of geometry and observation. It is not based on how long light travels, or how far humans can imagine, but on how stars actually move in the sky when viewed from Earth's orbit. This is why the parsec feels strange. It is not designed for intuition. It is designed for truth. In the next part, we will look closely at why brightness lies, why light years are not measurement tools, and how astronomers learned, slowly and painfully, that distance in space must be earned, not assumed. Once astronomers accepted that stars were unimaginably distant, a second problem appeared almost immediately. Even if distance could be measured, most of the clues people naturally relied on turned out to be deeply unreliable. Brightness, size, and clarity, things that work perfectly well on Earth, completely fall apart in space. Brightness is the biggest offender. Your brain assumes that brighter things are closer and dimmer things are farther away. This assumption works because, in everyday life, objects usually have roughly comparable intrinsic brightness. A nearby streetlight looks brighter than one down the road. A flashlight in your hand looks brighter than one across a field. Distance and brightness are linked closely enough that your intuition rarely gets confused. Stars break this relationship in the most aggressive way possible. Some stars are naturally thousands or even millions of times brighter than others. A massive blue star far across the galaxy can easily outshine a small red star that sits relatively close to us. From Earth, they may appear equally bright, or the distant one might even look brighter. This means brightness alone tells you almost nothing about distance. It is like standing on a dark beach and seeing two lighthouses. One could be 10 miles away and powerful, the other 2 miles away and weak. Without knowing how strong each lighthouse is, brightness gives you no reliable clue. Astronomers call this the difference between apparent brightness and intrinsic luminosity. Apparent brightness is what you see. Luminosity is how much energy the object actually produces. Distance scrambles the relationship between the two. For centuries, this confusion stalled astronomy. Without knowing distances, astronomers could catalog stars but not truly understand them. They could describe the sky but not explain it. The light year eventually entered the conversation as a way to communicate just how far away things really were. A light year is the distance light travels in 1 year, about 5.9 trillion miles, or roughly 9.5 trillion kilometers. As a storytelling tool, the light year is excellent. It instantly conveys vastness. Saying that a star is 100 light-years away tells the listener that the light reaching their eyes tonight left that star when the Roman Empire was still around. That idea sticks. But scientifically, the light year is clumsy. It mixes time and distance in a way that feels intuitive but becomes awkward in calculations. Astronomers measure angles, brightness ratios, and geometry, not travel times. When you start working with parallax, orbital motion, and trigonometry, the light year is not a natural unit. It has to be converted constantly. This is similar to measuring the length of a room by asking how long it would take a snail to cross it. You could do it, but why would you? Astronomers wanted a unit tied directly to observation, not storytelling. The breakthrough came from realizing that Earth itself could serve as one end of a cosmic measuring tape. As Earth orbits the Sun, our viewpoint shifts by about 300 million kilometers over 6 months. Nearby stars appear to wobble slightly against the background of distant stars. This wobble, parallax, is tiny, but it is measurable. The smaller the wobble, the farther away the star is. The larger the wobble, the closer it is. This is pure geometry. No assumptions about brightness required. Here is where the parsec enters quietly and decisively. A parsec is defined as the distance at which a star would show a parallax angle of exactly 1 arcsecond when observed from opposite sides of Earth's orbit. An arcsecond is an absurdly small angle, 1/3600th of a degree. To put that into perspective, it is roughly the apparent size of a coin seen from several miles away. At 1 parsec, the geometry lines up cleanly. The math becomes simple. The universe finally offers a ruler that fits the problem. This is why astronomers love the parsec, even if everyone else finds it irritating. The parsec is not based on light's speed, human perception, or convenience. It is based on how the universe actually behaves when observed carefully. Once distances could be measured in parsecs, the structure of space began to reveal itself. Stars were no longer dots on a dome. They became points in a three-dimensional map. The Milky Way gained thickness. Star clusters gained depth. The galaxy stopped being a painting and started becoming architecture. And, just as importantly, astronomers could finally test their theories. They could calculate true stellar sizes, masses, and lifetimes. They could compare models to reality. Distance unlocked physics. In the next part, we will slow down and unpack the geometry itself. What parallax really means, why the angles are so small, and why measuring them pushed technology to its absolute limits for more than a century. To really understand why the parsec exists, we need to slow down and sit with parallax for a moment, because this tiny effect carries an enormous amount of responsibility in astronomy. It is the foundation on which almost every other distance measurement is built. Parallax is, at its heart, something you already understand intuitively. hold your thumb out in front of your face and close one eye. Then switch eyes. Your thumb appears to jump sideways against the background. That jump happens because each eye views your thumb from a slightly different position. Your brain uses that difference to judge distance. Now, imagine doing the same thing. But instead of using your two eyes, you use Earth at two opposite points in its orbit around the Sun. 6 months apart, Earth is about 300 million kilometers away from its previous position. That baseline becomes your eye separation. Nearby stars shift slightly against the background of much more distant stars. That shift is parallax. The crucial word here is slightly. Even the closest star beyond the Sun, Proxima Centauri, shows a parallax of less than 1 arcsecond. That means the apparent shift is smaller than the width of a human hair seen from several meters away. For most stars, the shift is far smaller than that. This explains why parallax was impossible to detect until telescopes reached extraordinary levels of precision. Early astronomers suspected it should exist, but they simply could not see it. For centuries, stars stubbornly refused to budge. This failure caused real confusion. Some astronomers used the lack of observable parallax as evidence that Earth did not move at all. If Earth orbited the Sun, they argued, parallax should be obvious. Since it wasn't, maybe Earth was stationary and the universe revolved around it instead. The universe didn't care about that debate. The stars were just too far away. Once telescopes improved enough in the 19th century, parallax finally revealed itself. The first successful stellar parallax measurement was made in 1838 by Friedrich Bessel. The shift he measured was tiny, but it was real. And it changed everything. For the first time, astronomers had a direct geometric distance to a star. This is where the parsec quietly becomes unavoidable. If you define distance in terms of parallax angle, the math becomes elegantly simple. A star with a parallax of 1 arcsecond lies at 1 parsec. A star with half an arcsecond lies at 2 parsecs. A star with 1/10 of an arcsecond lies at 10 parsecs. Distance equals 1 divided by parallax. Clean, direct. No storytelling required. The parsec isn't strange because astronomers wanted it to be. It is strange because the universe is built on geometry, not intuition. But there is a limit to this method, and it appears quickly. As stars get farther away, their parallax angles shrink below what Earth-based telescopes can reliably measure. Atmospheric turbulence alone blurs images by more than the parallax shift of most stars. Even perfect optics cannot overcome a shimmering atmosphere. This limitation meant that, for a long time, parallax could only measure distances to stars within a few hundred parsecs. Beyond that, the ruler simply stopped working. Astronomers responded the way scientists always do. They built ladders. Once distances to nearby stars were known, those stars could be used to calibrate other distance indicators. Certain types of stars behave predictably. If you know how bright they truly are and how bright they appear, you can infer distance. But all of those methods depend on parallax at the bottom. If the foundation is wrong, the entire structure collapses. This is why parallax measurements are treated with almost obsessive care. Space telescopes like Hipparcos and Gaia were built largely to escape Earth's atmosphere and measure parallax with unprecedented accuracy. Gaia, in particular, has measured distances to more than 1 billion stars, mapping the Milky Way in 3 dimensions with parsecs as its fundamental unit. Thanks to this, the galaxy is no longer a vague smear of light. It has spiral arms, gaps, thickness, and structure. Star clusters stretch and curve. Stellar streams reveal ancient collisions. None of this would be visible without parsec-based distances. The irony is that the parsec, which feels abstract and awkward to most people, is one of the most concrete units in science. It is literally anchored to Earth's orbit and the geometry of space. In the next part, we'll widen the view and explore how parsecs scale up, kiloparsecs, megaparsecs, and why the same unit that measures nearby stars also quietly governs our understanding of galaxies, clusters, and the large-scale structure of the universe. Once astronomers realized that a single parsec could map the nearby stars, the next logical step was unavoidable. The universe did not stop at a few dozen parsecs, it kept going. Farther than parallax could reach, farther than intuition could comfortably follow. So astronomers did what humans always do when a ruler feels too small. They stacked it. 1,000 parsecs became a kiloparsec. 1,000,000 parsecs became a megaparsec. 1,000,000,000 parsecs became a gigaparsec. Same ruler, same geometry, just stretched across a much larger stage. At first glance, this looks like a mathematical convenience, but it turns out to be something much deeper. Using parsecs at every scale keeps distance measurements internally consistent across the entire universe. The Milky Way, for example, is about 30 kiloparsecs across. That number is not arbitrary. It comes from mapping star positions, clusters, gas clouds, and spiral arms using parsec-based distances. When astronomers say the Sun is about 8 kiloparsecs from the galactic center, they are placing us within a precise three-dimensional map, not a rough sketch. To make that number feel less abstract, imagine the Milky Way as a city about 30 kilometers wide. The Sun would sit roughly 8 kilometers from downtown, not at the center, but not in the outskirts either. That position explains why the galaxy looks the way it does from Earth. Our view is biased by where we sit. As distances increase beyond the Milky Way, the parsec becomes even more important. Nearby galaxies are measured in hundreds of kiloparsecs. The Andromeda Galaxy, our closest large neighbor, sits about 780 kiloparsecs away. That distance comes from multiple methods, but all of them are calibrated against parsec-based measurements closer to home. On larger scales, galaxy clusters stretch across megaparsecs. These clusters are not random piles of galaxies. They form along filaments, vast cosmic threads connecting dense regions like beads on invisible strings. The distances between these structures, their sizes, and their motions are all described in megaparsecs. This is where the parsec quietly transforms from a measuring stick into a language. When astronomers talk about the large-scale structure of the universe, they describe voids tens of megaparsecs wide, filaments hundreds of megaparsecs long, and superclusters spanning enormous volumes of space. Without a consistent unit like the parsec, these patterns would be difficult to compare or even recognize. But there is another layer to this story. As distances increase, something strange happens. Space itself begins to matter. At local scales, distances behave the way you expect. Objects move through space. But at cosmic scales, space expands. Galaxies are not simply flying away from one another, the space between them is stretching. This is where parsecs become essential again. Expansion rates are measured in kilometers per second per megaparsec. That unit only makes sense if megaparsecs are your standard ruler. It tells you how much faster galaxies recede as distance increases, not because they are moving faster, but because more space lies between them. Think of it like dots on a balloon being inflated. Nearby dots drift apart slowly. Distant dots separate much faster. The parsec allows astronomers to quantify this effect precisely. Without it, cosmic expansion would be a poetic metaphor instead of a measurable phenomenon. There is also a subtle psychological advantage to using parsecs at every scale. It prevents the mind from resetting its expectations too often. When everything from nearby stars to distant galaxies is measured in the same underlying unit, the universe feels continuous rather than fragmented. Light years, while intuitive, tend to break this continuity. A few light years feels manageable. Millions feel absurd. Billions become meaningless. The parsec sidesteps that emotional overload by remaining stubbornly geometric. A parsec doesn't care how long light takes to travel. It only cares about angles and baselines. This makes it a surprisingly calm unit in a universe that constantly challenges human intuition. In the next part, we'll look at why the parsec feels so counterintuitive to non-astronomers, how it clashes with everyday thinking, and why it persists anyway despite constant confusion. By the time most people first encounter the word parsec, it already feels suspicious. It doesn't sound like a distance. It sounds like a particle, a medical term, or something invented for a science fiction movie. And, in a way, that reaction makes sense. The parsec is not built for human intuition. It was never meant to be. Humans are comfortable with distances we can imagine traveling. Miles, kilometers, hours on a highway, days on a plane. Even a light year, while enormous, sneaks in a familiar concept: time. You can think, if light travels for a year, that's far. You may not feel the distance, but you at least understand the ingredients. The parsec offers no such comfort. It does not tell you how long a journey would take. It does not tell you how fast something is moving. It does not relate to anything you've ever experienced directly. Instead, it quietly asks you to picture geometry on a scale that your brain was never designed to handle. At its heart, the parsec is defined by an angle so small that it barely exists in daily life. 1 arcsecond is 1/3600th of a degree. To visualize that, imagine dividing the width of the full moon into about 800 tiny slices. Then take one of those slices and divide it again. That's the angle involved. Now imagine using that angle to measure a star. The reason this feels unnatural is not because the parsec is strange, but because the universe is. Human intuition evolved to judge distances measured in footsteps, not astronomical baselines. Our brains are excellent at estimating where to throw a ball or how far away a tree is. They are terrible at angles that only become meaningful across hundreds of millions of kilometers. Astronomers know this, and they accept it. They use parsecs not because they are intuitive, but because they are reliable. A parsec does not depend on assumptions about how bright something should be. It does not rely on models of stellar evolution. It does not care whether a star is young, old, dusty, or unusual. If you can measure its parallax, you can measure its distance. That makes the parsec brutally honest. This honesty becomes critical when astronomers start stacking distance measurements. Every larger cosmic ruler is calibrated using smaller ones. If the first step is wrong, everything built on top of it collapses. Think of it like building a skyscraper. If the foundation is off by a few centimeters, the top floors end up meters out of place. Parsec-based measurements are the foundation. They anchor all other distance methods to something solid. That said, astronomers are fully aware that parsecs confuse people. Even within science communication, light years are often used for public explanations. But behind the scenes, the math almost always happens in parsecs. It's similar to cooking with weight instead of cups. Cups feel friendly. Grams feel precise. When accuracy matters, you use the scale, even if it feels less intuitive. There's another reason parsecs persist. They scale effortlessly. Once you accept a parsec, everything else follows naturally. Kiloparsecs describe galaxies. Megaparsecs describe galaxy clusters. Gigaparsecs describe the observable universe. The same geometric logic stretches across cosmic history. Light years, by contrast, tend to fragment understanding. You switch mental gears constantly. Stars are light years away. Galaxies are millions of light years away. The universe is billions of light years across. Each jump feels disconnected. Parsecs keep the conversation continuous. They also subtly remind astronomers of something important. Distance in astronomy is not just about how far something is, but how we know how far it is. Every parsec measurement carries with it an implicit question. What method was used? What assumptions were involved? And how reliable is the result? In that sense, the parsec is not just a unit. It's a statement about epistemology. It says, this distance is grounded in geometry. In the next part, we'll explore how parsecs fit into the larger distance ladder, how astronomers measure distances far beyond parallax, and why everything still circles back to this strange, stubborn unit that makes no sense until you need it. Once astronomers accept that parsecs are unavoidable for nearby stars, the next question becomes uncomfortable very quickly. What happens when parallax stops working? Because it does stop working. Parallax is wonderfully honest, but it has a short reach. As stars get farther away, their apparent wobble shrinks. Eventually, the shift becomes smaller than the limits of even our best instruments. It's like trying to notice the thickness of a human hair from miles away. At some point, geometry simply runs out of resolution. This is where astronomy becomes a careful game of trust. Astronomers build what's known as the cosmic distance ladder. It's called a ladder because no single method reaches from Earth to the edge of the universe. Instead, each rung relies on the previous one for calibration, and parsecs sit firmly at the bottom. The first rung is parallax. Using Earth's orbit as a baseline, astronomers measure distances to nearby stars in parsecs. These measurements are as direct as astronomy gets. No guesswork, just geometry. Once those distances are known, astronomers can study certain types of stars whose intrinsic brightness is predictable. Cepheid variable stars are the classic example. These stars pulse in brightness at a steady rhythm. The slower the pulse, the brighter the star truly is. Here's the key idea. If you know how bright something really is, and you measure how bright it appears, you can calculate how far away it must be. But how do we know how bright cepheids truly are? Because we measured nearby ones using parsecs. Parallax distances anchor the brightness of these stars. That allows cepheids to become the next rung on the ladder, extending distance measurements to nearby galaxies. Then comes the next step, type Ia supernovae. These stellar explosions shine with nearly uniform peak brightness. When one goes off in a distant galaxy, it acts like a cosmic flare, visible across vast stretches of space. Again, their usefulness depends on calibration, and again, that calibration ultimately traces back to parsecs. This chain continues outward. Galaxies, clusters, superclusters. Each rung relies on the one below it. If the first rung were wrong, everything above it would wobble. This is why astronomers obsess over parsec accuracy. A tiny error in nearby distances doesn't stay tiny. It grows as measurements stack on top of one another. By the time you reach billions of light years, a small mistake near Earth can turn into a massive misunderstanding about the size, age, and expansion rate of the universe. This isn't theoretical. It's happening right now. One of the biggest debates in modern cosmology is the Hubble tension. Different methods of measuring the expansion rate of the universe give slightly different answers. One method uses nearby galaxies calibrated through parsecs and Cepheids. Another uses early universe signals from the cosmic microwave background. They don't quite agree. And that disagreement may trace all the way back to how well we understand the first few rungs of the ladder. That's why missions like Gaia matter so much. Gaia is measuring stellar parallaxes with unprecedented precision, refining parsec-based distances for more than 1 billion stars. It's not flashy, it doesn't take dramatic pictures, but it is quietly rewriting the foundation of cosmic measurement. If Gaia adjusts distances by even a few percent, entire cosmological models must be reevaluated. This highlights something subtle but important. The parsec isn't just a distance unit. It's a calibration tool. It tells astronomers not only how far away something is, but how confident they can be in everything that comes after. In everyday life, we rarely think this way. We don't question whether a mile is truly a mile. But in cosmology, every unit carries a history. Every measurement carries uncertainty. The parsec earns its place by being the least assumptive step in a long chain of inference. In the next part, we'll zoom out further and look at how parsecs scale up to describe galaxies and the universe itself. Why megaparsecs dominate cosmology, and how this strange unit becomes surprisingly elegant once you leave human scales behind. Once you step beyond individual stars and even beyond individual galaxies, something interesting happens to your sense of distance. Light years begin to feel small. Parsec-based units stop being awkward and start becoming practical. At the scale of galaxies, astronomers rarely talk about parsecs anymore. They talk about kiloparsecs and megaparsecs. A kiloparsec is 1,000 parsecs. A megaparsec is 1,000,000 parsecs. These aren't dramatic leaps invented to sound impressive. They're a response to scale. The Milky Way is about 30 kiloparsecs across. Saying it's about 100,000 light-years wide is perfectly correct. But when you start comparing galaxies, kiloparsecs fit more naturally into equations and models. Spiral arms span a few kiloparsecs. Galactic disks have thicknesses measured in hundreds of parsecs. Stellar halos stretch tens of kiloparsecs outward. At this level, the parsec feels like a sensible building block. Then comes the next leap. Galaxy groups, clusters, and the large-scale structure of the universe are measured in megaparsecs. This is where the unit truly settles into its role as a cosmological language. the distance between major galaxy clusters is typically a few megaparsecs. The vast filaments of galaxies that thread the universe stretch for tens or hundreds of megaparsecs. The voids between them, enormous regions of near emptiness, can span dozens of megaparsecs. When cosmologists describe the universe, they are not thinking in terms of stars or even galaxies. They are thinking in terms of patterns, webs, sheets, nodes, voids. Megaparsecs make those patterns readable. Here's an analogy. Imagine trying to describe the layout of a continent using inches. You could do it, technically, but every sentence would be unbearable. Switch to miles, and suddenly geography makes sense. Rivers, mountain ranges, coastlines, they emerge naturally. Parsecs do the same thing for cosmic geography. At the largest scales, the universe looks smooth. Galaxies cluster together, but beyond about 100 megaparsecs, matter spreads out evenly. This scale, sometimes called the homogeneity scale, is crucial to cosmology. It tells us when local structure gives way to global simplicity. And again, parsecs sit quietly underneath all of it. When astronomers measure how fast galaxies are moving away from us, they express expansion as kilometers per second per megaparsec. This is the Hubble constant. It doesn't tell you how fast a galaxy is moving in isolation. It tells you how much faster galaxies recede for every additional megaparsec of distance. This unit choice is not arbitrary. It directly connects observed redshift to distance measured in parsecs. The entire framework of cosmic expansion is built around this scaling. In this context, light years become clumsy. A value like 70 kilometers per second per megaparsec carries immediate meaning for cosmologists. Converting it into light years adds steps without adding clarity. This is one reason parsecs persist despite sounding strange to newcomers. They are mathematically efficient. They align with observation, theory, and geometry in ways light years do not. There's also a philosophical shift that happens here. When distances grow to megaparsec scales, the universe stops feeling like a collection of objects and starts feeling like a system. Individual stars disappear. Even galaxies blur into statistical entities. What matters are averages, densities, fluctuations. At this scale, space itself becomes the subject. Parsecs are not just measuring where things are, they are measuring how space behaves. The expansion of the universe stretches parsec-scale distances over time. A megaparsec today was smaller in the past. When cosmologists simulate the universe's evolution, they track how regions measured in megaparsecs grow, compress, and reorganize. This turns the parsec into a time-sensitive unit. It's not just a ruler. It's a snapshot of cosmic geometry at a particular moment in history. And that brings us to something even stranger. At the largest observable scales, distances measured in megaparsecs begin to lose their classical meaning altogether. Expansion accelerates. Horizons form. Regions slip beyond causal contact. The parsec remains the unit we use, but what it represents becomes less intuitive. In the next part, we'll confront that directly. We'll look at where parsecs meet cosmic horizons, why distance in an expanding universe is more complicated than it sounds, and how this simple unit becomes tangled with time, relativity, and the limits of observation itself. As we move deeper into cosmic scales, something subtle but important happens to the idea of distance itself. Up to this point, we have been treating parsecs as if they were ordinary lengths, like miles on a highway or kilometers between cities. But once the universe's expansion enters the picture, distance stops being a single, well-defined thing. In an expanding universe, there are several different ways to measure how far away something is, and they don't always agree. Astronomers still use parsecs, but the meaning of a parsec depends on what question you are asking. One way to think about distance is simple: how far away an object is right now. This is called proper distance. If you could freeze the expansion of the universe at this instant and stretch a measuring tape through space, the number of parsecs you'd count would be the proper distance. But there's a problem. You can't actually do that. The universe doesn't pause while you measure it. Another way to define distance is based on light travel time. How many years did the light take to reach us? This sounds intuitive, but in an expanding universe, light travels through space that is itself stretching. So, the distance the light traveled when it was emitted is not the same as the distance between us and the object today. This leads to a strange but real situation. A galaxy can be said to be 10 billion light-years away based on light travel time. Yet, its current proper distance might be over 20 billion light-years in parsecs. Both numbers are correct. They just answer different questions. Parsecs remain useful because they fit neatly into the equations that describe expansion. Cosmologists describe the universe using a scale factor, a number that tells you how much space has stretched since a given moment in the past. Distances in parsecs expand with this scale factor. Here's an analogy. Imagine dots drawn on a balloon. As the balloon inflates, the dots move farther apart, even though none of them are moving across the surface. The distance between dots depends on when you measure it. Parsecs measure the spacing between dots on the balloon's surface, while the scale factor tells you how inflated the balloon is. This matters because beyond a certain distance, expansion becomes so strong that objects recede from us faster than light. Not because they're breaking the speed limit of relativity, but because space between us and them is growing too quickly. These distances are still measured in megaparsecs. When astronomers say a galaxy is receding at thousands of kilometers per second, they are usually calculating that velocity from its distance in megaparsecs multiplied by the Hubble constant. The parsec is embedded in the expansion law itself. Then we reach cosmic horizons. There is a limit to how far we can see, not because the universe ends, but because light has only had a finite amount of time to travel. This boundary is called the observable universe, and its radius is about 46 billion light-years, or roughly 14,000 megaparsecs. That number alone shows why parsecs dominate cosmology. Writing 14,000 megaparsecs is far more manageable than juggling tens of billions of light-years in equations. But here's the deeper twist. Regions beyond this horizon still exist. They are simply unreachable. Their distances, measured in parsecs, are real in theory, but unknowable in practice. At this point, the parsec becomes a conceptual tool rather than a measurable one. It helps us describe a universe that extends beyond observation, beyond experiment, and beyond confirmation. Yet we keep using it, because even when we cannot see farther, we can still model farther. Parsecs allow cosmologists to simulate the universe on scales that dwarf our observational reach, tracking how matter, energy, and geometry behave across unimaginable distances. In the next part, we'll explore how this unit, born from a humble triangle, became essential for mapping a universe whose most important distances may never be directly measured at all. By this stage, the parsec has quietly transformed from a clever measuring trick into something closer to a language. It's not just a unit anymore. It's how astronomers think about structure, scale, and history in the universe. One of the most important places where parsecs shape our understanding is in how matter organizes itself on the largest scales. When astronomers map the universe, they don't see stars sprinkled evenly through space. They see filaments, walls, clusters, and vast empty regions called voids, all stretching across tens or hundreds of megaparsecs. These structures are so large that if we tried to describe them in everyday terms, the numbers would become meaningless. Saying a cosmic filament is 300 million light-years long doesn't really help your intuition. But saying it spans about 100 megaparsecs immediately places it in the framework used by simulations, equations, and observations. This is where parsecs become essential for comparing theory and reality. Modern cosmology relies heavily on simulations, enormous computational models that evolve virtual universes from the early moments after the Big Bang to the present day. These simulations divide space into grids measured in kiloparsecs or megaparsecs. Galaxies form inside dark matter halos measured in tens or hundreds of kiloparsecs. Galaxy clusters extend over several megaparsecs. Superclusters span tens of megaparsecs. Without the parsec, none of this would fit neatly together. Think of it like building a city in a simulation game. You wouldn't measure the width of a road in miles and the distance between cities in inches. You choose units that scale logically. Parsecs do exactly that for the universe. They also help us understand time. Because light takes time to travel, looking farther away means looking further into the past. When astronomers say they are observing a galaxy at a distance of several gigaparsecs, they are also saying they are seeing that galaxy billions of years ago. Distance in parsecs becomes a timeline. This connection between space and time is baked into the equations of cosmology. When scientists reconstruct the universe's history, they track how distances between objects changed over time, measured consistently in parsecs while the scale factor evolves. Even the cosmic microwave background, the faint afterglow of the Big Bang, is described in terms of distances measured in megaparsecs. The size of tiny temperature fluctuations in that ancient light corresponds to physical scales that were once a few hundred kiloparsecs across, stretched by expansion to hundreds of megaparsecs today. Once again, parsecs quietly hold everything together. But perhaps the most surprising role of the parsec is psychological. It forces astronomers to abandon human-centered intuition. A parsec is not a distance you walk, drive, or fly. It is a distance you infer. You don't measure it directly. You calculate it from angles, brightness, motion, and redshift. That changes how you think about reality. In astronomy, most things are never touched or visited. They are reconstructed from light and geometry. The parsec embodies that mindset perfectly. It reminds us that our knowledge of the universe is built from careful inference rather than direct experience. And despite sounding abstract or even confusing, the parsec is actually deeply practical. It allows different measurement techniques, parallax, standard candles, redshift, to connect smoothly across scales. It is the bridge between nearby stars and the edge of the observable universe. So, while it may seem strange at first, even unnecessary, the parsec is one of the most human tools we've invented for understanding something profoundly non-human. In the final part, we'll step back and ask the bigger question: what the existence of a unit like the parsec says about our relationship with the universe itself, and why misunderstanding it might be a sign that we're finally starting to think on cosmic terms. By the time you reach the far end of this idea, it becomes clear that the parsec is not strange because it is complicated. It is strange because it forces us to let go of everyday thinking. The universe simply does not scale down to human experience, and the parsec exists because our intuition fails long before the stars do. When astronomers adopted the parsec, they weren't trying to confuse anyone. They were trying to make sense of a universe that refuses to fit into familiar categories. Angles matter more than rulers. Light matters more than touch. Geometry matters more than distance walked. The parsec is a compromise between what we can observe and what we want to understand. And that compromise turned out to be incredibly powerful. With parsecs, astronomers could finally compare stars of different brightness without guessing their true size. They could build the first reliable star maps. They could place our sun inside a spiral galaxy rather than at the center of everything. They could discover that galaxies cluster, that the universe expands, and that its structure stretches across distances so vast they challenge language itself. Every major step in modern cosmology relies on parsecs somewhere in the background. Even debates about dark energy, cosmic acceleration, and the ultimate fate of the universe depend on measuring how distances in megaparsecs change over time. When scientists argue about whether expansion is slowing or speeding up, they are really arguing about how parsec-scaled distances evolve as the universe ages. In that sense, the parsec is not just a unit of space. It is a tool for measuring cosmic change. It also quietly reminds us of our limitations. We cannot stand between stars and hold a measuring tape. We cannot see depth directly in the sky. We infer distance from tiny shifts, subtle dimming, and faint spectral clues. The parsec encodes that humility. It acknowledges that our understanding of the universe is indirect, built from patience and inference rather than certainty. And yet, that indirect approach works astonishingly well. Using parsecs, we can estimate the size of galaxies we will never visit, map structures we will never cross, and trace cosmic history back more than 13 billion years. Few concepts in science offer such reach with such simplicity once understood. If the parsec feels unintuitive, that's not a failure of explanation. It's evidence that your brain evolved for survival on Earth, not navigation among stars. The real achievement is that we found a way to bridge that gap at all. In the end, the parsec makes no sense only if we expect the universe to make sense on human terms. But when we accept that space plays by its own rules, the parsec becomes exactly what it needs to be. A quiet, elegant translation between our limited viewpoint and an unimaginably large reality. And perhaps that is its greatest lesson. Understanding the universe often means learning new ways to think, not just new facts. The parsec doesn't just measure distance. It measures how far human curiosity has learned to stretch. far enough, it turns out, to map the cosmos itself.